Today we focused on spectroscopy, and we've been asking ourselves what exactly is molecular spectroscopy, and we'll be focused on three types of this spectroscopy, that is infrared or vibration spectroscopy, mass spectroscopy, and nuclear magnetic resonance. The two nuclei we're concerned about are the protons and the carbon-13s. You can see here, for example, we have a molecule pi star, so it's a pi system, and you can imagine there's an energy difference here, and that energy difference equals to delta E equals to h nu, where h is Planck's constant and nu is the frequency of light. So if you imagine hitting this molecule with this particle of light, then those two electrons in the ground state will be excited, and you would have promotion of one electron to pi star. This promotion realizes absorption of that h nu. So we got to associate this particle of light, with also the wavelength related to that light because of Einstein's wave-particle duality. There's not a lot that we can do with that light except we can reflect it, absorb it, or emit it of some sort, So it's all to do with some type of absorption, alright? And the absorption of said molecule, will tell us what the content of that molecule is. So you can see here, associated with that wave is of course the wavelength, and of course associated with that same species, that light, is the frequency as we stated before, and Planck's constant of course 6.63 times 10 to the minus 34 seconds. There is a direct proportionality between energy and frequency, and there's an inverse proportionality with wavelength. You can see that we can classify this radiation. We can classify it spectral, so from X-ray all the way through to radio. We can classify spectroscopically, and of course we're looking at such electronic spectra or vibration spectra and spin, and of course we can look at applications such as that to do with absorption spectroscopy, and so photochemistry, photosynthesis, and therapeutics, for example. You can see here the electromagnetic spectrum, right? And you can see there's an inverse proportionality between wavelength and frequency, and a direct proportionality between frequency and energy, right? So as we increase energy, we increase frequency, and you can see there's a decrease in wavelengths. Look carefully, there's a tiny sliver here belonging to the visible, and of course below the visible we have infrared, and above we have ultraviolet. Note that herein we can ask ourselves simple questions such as, which is the highest in energy? That's quite simple to figure out. What I would have asked in an exam would be to rank these energies. And so here we can look at the regions and look at the energy transitions involved, and you can see the ones that we're concerned with. Ultraviolet will be electronic, infrared is vibrational, and of course radio is nuclear and electronic spin. Where is mass spec? The reason why mass spec is absent from here because that's not a true spectroscopic technique, and we'll be looking at that later. Exactly. So let's look at vibration spectroscopy, also known as infrared spectroscopy, and that's to do with the vibration of bonds. It can be either bending or stretching vibrations. right? We use these to identify functional groups in the molecule. We can either do this qualitatively, do spectral matching, or we can do quantitative analysis, yeah, via absorption. That will give us, yeah, things like concentration, etc., etc. You can see this is an infrared spectrum. In the x-axis, you can see that we have a frequency scale called wave numbers, not exactly linear. And then, of course, you can see that there is difference in intensity of these bands. Right. In the y-axis, we have transmittance. Transmittance, of course, is inversely proportional to absorption. So here we're increasing absorption. At the same time, we have strong absorption. We have low transmissions. Make sense? Right. The shape is also important because you can see this is very broad and strong. So the intensity is strong. The shape is broad. Here we have it's medium and it's sharp. Yeah, it's weak here and sharp. Yeah, it's fairly weak here and sharp. Fairly weak but broad, and so on. These are the type of stretching that you have. You can see it can be symmetric or asymmetric, and you can also bend and in plane or out of plane. So these are the types of vibrations that you'll see in your spectrum. Fortunately for us, a lot of these energies that we absorb for these type of vibrations are equal, yeah, or in the same region, and so yeah, we do not have to elucidate too many lines. Why? We take a quantum mechanical approach to this work, and we look at the bond. Yeah, we can look at a typical diatomic molecule, yeah, as a spring, yeah, connecting the two nuclei. So we can therefore use Hooke's law. Realize that with a spring you're compressing and stretching with a force constant, and of course there's a difference in the distance, yeah, every time you stretch and compress. And of course we're looking at the two different masses, M1 and M2. This is the equation associated with an harmonic species, because remind yourself, right, that this simple harmonic, yeah, is this curve, and the actual molecule is an harmonic. But we can use a simple harmonic to describe exactly what we're working with. Do not get too concerned about this, because if you notice carefully, right, there is this constant, which is just a couple of numbers. We can just get rid of that. We can ignore that. This here means a square root, so we can, yeah, easily get rid of that for the time being. And then once you sort of reduce it, you can see that the frequency is directly proportional to the force constant, i.e. the frequency is directly proportional to the strength of the bond. So as you increase bond strength, then of course you will increase the frequency. You can also see that frequency is inversely proportional to the reduced mass. And the reduced mass looks a bit complex, but it's not, because think about it for a second. The reduced mass is really the product of the two masses divided by the sum of the two masses. I want you to compare carbon hydrogen to carbon deuterium, which deuterium is chemically equivalent to hydrogen. This is of course mass 12. Let's get rid of that. This is very naughty. This is 1, this is 12, that's 2. So the product here for CH is 12, for CD of course is 24. The sum M1 plus M2 is 13 here, and for the CD it's 14. You can see that denominators are not much difference, and so therefore note therefore that we can easily state that the frequency is inversely proportional to the mass. So here you can see that, yeah, that the larger the mass, yeah, then of course the greater so let me repeat that. Realize that the larger the mass, then of course the lower the frequency. You can see here where we have the higher, the larger the force constant, i.e. the bond strength, then of course the lower the frequency. So let me repeat that. The larger the bond strength, then the higher the frequency. Make sense? So herein we're looking at the 4 primary regions of the infrared spectra, and I want you to focus on the OH, NH, CH. So these are the atoms attached to the hydrogen, and then of course the triple bonded region, which is in the 2000 region, and the double bonded region, which centered around 1700. Below that, of course, we will have the fingerprint region, and the fingerprint region we're not really concerned about in this course. You can see here a summary of some hydrocarbons. Here we're looking at the alkenes and alkynes, and what you need to do here is draw a line, yeah, at 3000 and see exactly what's to the left of it. You can see here the alkenes, the vinylic CH will appear as a splinter, and then of course the alkalinic species will appear standalone. Of course there is a difference because of the bond strength. Think about exactly what increases the strength of the alkyne CH. You can see there can be intensities differences as well. One difference, yeah, is due to the dipole. The stronger the dipole, the larger the dipole, the stronger the intensity. So if you compare the carbonyl to the alkene, you can see exactly why. So herein you can see that looking here at a regular alkane, you can see the CH centered around 3000, just below 3000. There is here, you can see there is broadening of the bond compared to when you have hydrogen bonding, and of course if it's a molecule in the gas phase, then of course we'll also have sharper signals. And herein you can see, for example, the OH, yeah, which has hydrogen bonding, yeah, is quite broad, while the alkyne CH quite sharp. Look at the NHs for both the secondary and primary amines. These are fairly broad but weaker because they're not that polar, and of course, yeah, you can see there's a difference between the secondary and the primary. And look at the vanillic CH and the aromatic CH. You can see that once we go beyond 3000, then of course you can see that splinter. Yeah, it's due to this bonding here. Analyzing the IR spectrum, yeah, we'll be looking at the hydrocarbons. Actually, we just probed them a while ago. And then we can look at, say, for example, the alcohol, which has had hydrogen bonding. We look at the carbonyls, of course, so the aldehyde ketones and carboxylic acids. And of course, we'll look at this guy here, which is in the triple bonded region, and amines. So you can see, we just looked at the octane. All we can see here is that CH. So it's significant to us, but with the alkene, you can see the CH here is quite, it's a medium peak and it's quite sharp. On the other hand, the CH of the species, so this was a C double bond C, I should say, but you can see that the CH itself, yeah, is just beyond the 3000, yeah, alright, as a splinter. For the alkyne, yeah, you can see there's two peaks. This is a terminal alkyne, by the way. For some reason, infrared can't see internal alkynes, but terminal alkyne, you can see that the C triple bond C is in the triple bonded region, 2000s, and of course the CH, of course, beyond, is way beyond the 3000. You see, it's 3000, so it's here around 3200. For the alcohols, you can see the OH, again beyond 3000, but this time around it's fairly broad. Fairly broad, and it's fairly strong because not only is it quite polar, yeah, but of course it is hydrogen bonding. The carbonyl, of course, is very polar, and it's going to be in the C double bond or C double bond. It's going to be in the double bonded region. In this case here, it's in around 1710. You can't miss it. So, for example, you can see here with the aldehyde, you can see this CH. It's really at a weird place. But what's more important is this C double bond. Centered around 1700. Ketones, on the other hand, does not have a CH, so there's no CHs in this region here. But of course, we can see that C double bond very intense, yeah, in the double bonded region. You can see here the carbonyl. The carbonyl also has that C double bond O, but along with that C double bond O, we have, of course, the OH. But for reasons we're probing later on in later chapters, we'll see that the carboxylic acid has extensive hydrogen bonding, and because of that, the OH is much broader. See, it's centered around 3000, but it's much broader than the alcoholic OH. The nitriles, of course, yeah, similar to the C triple bond C, yeah, sits in the triple bonded region, yeah, 2100. But of course, it's a little bit more polar than a alkyne, and so therefore you'd expect it to be a bit more intense. So ask yourself, what functional group do we have here? First of all, we'd have to look, yeah, and look at exactly what's going on. You can see if you look beyond 3000, there's nothing, right? So it can't be an alcohol. If you look in the triple bonded region here, 2000s, there is no straight, so that's not an alkyne. So yeah, you can see for carboxylic acid, of course, you'd expect something to be in to be an OH, intense OH, That's not existing, so that's out as well. And so we're left with these guys here, because this is in the double bonded region. However, note, yeah, that this is a very intense peak. It's a very strong peak, and so this can't be a C double bond C. It is definitely a ketone. Make sense? So always analyze the fingerprint region. The fingerprint, well, we're not analyzing the fingerprint region actually. We should not say that. Sorry about that. We should analyze the functional group region. It's supposed to be functional group region. And look for double bonds or triple bonds, and then look for anything that's bonded to hydrogen, and draw a line, yeah, at 3000 and probe exactly what's to the left of it. Right? Then of course analyze the intensity in the shape of the bands. So for example here you can see that we looked at 6000 region, we see we got stuff going on, right? And of course we looked at the triple bonded region, there was nothing. And if you look at the XH region, you can see at 3000 there's this fella here, and so we know we have some sort of alkene. What about this one? Immediately you can go 3000 here, you will see immediately there's this fella here, right? And so it tells you there's an alcohol, because there's nothing going on in the both the double bonded region or the triple bonded region. Just above 3000 we see it's a broad peak. What about this one? Yeah, in the double bonded region we see something. There's nothing in the triple bonded region, and there's nothing above 3000. So what we're left with is an alkene or a carbonyl, and you realize that this is very, very, very strong peak, so it has to be a carbonyl. So the only thing that we can think of right now is the pentanol. Note, we have a nitrogen, yeah, and here you can see in the triple bonded region we have some sort of stretch, so we immediately know we have a nitrile, so we can draw various species that's associated with this guy. All right. Limitations of the infrared. Yeah, you can see that we cannot determine the structure on its own. It's quite difficult. We can elucidate some functional groups, but it's really tough. Yeah, because some of the signals are ambiguous. Yeah, and the absence of a signal is proof that the functional group is absent. Alright, so what we need to do is we need to go to another technique, and this is mass spectrometry. Mass spec, the true sense of the word, is not a pure spectroscopy technique, yeah, because it's not like we're using light to interrogate matter. Here's what we do, right? And yeah, we can use this, by the way, to a number of uses. As you can see here, we can talk about these in class. But what we have is we have an ionization source. In this case here, we're looking at electron ionization mass spectrometry, and we so we have we're looking at this fella here, this one. So we have an ionization source, and then of course we ionize our molecule, place it in the analyzer, and then of course we can detect it later on down the road. So here in our case we have our sample, yeah, introduced into a vacuum chamber, and of course we provide electrons which slam into our sample, so accelerated by these magnets into our sample, and then of course the sample itself yeah, the fragments of the sample is, yes, accelerated down this tube and then bent by this magnetic field. The deflection, yeah, that occurs is determined by the mass over charge, and it's kind of hard to get a +2 charge in mass spec. Usually we get a +1 charge, so most of these peaks are due to the mass of those fragments. So the compound is vaporized and ionized, and then the masses of the ions are detected and graphed. How does it work? We have an electron spanking an atom, a molecule, sorry, and then of course the molecule gets excited, and you can see that it loses an electron. So now we have a positively charged species, what we call a charged radical. Yeah, and in this case here, this is the molecular ion. This one is the molecular ion. So in this case it's M plus, and you can see fragmentation starts to occur. In this case here we lost a radical and one atom, and we're left with this species. So this is an N-1 peak. You can see also here, right, we lost, yeah, this fragment. So this is an M, this species here is an M-15 peak, meaning the molecular mass minus 15 mass units. Herein you can see we have other compounds. So for example, yeah, we can see here we have the propyl species, and the propyl is quite interesting because you can see that, yeah, we have M-15 here, we got the N-29 here, and of course we have the molecular ion itself here. Yeah, but we have some interesting thing. Here's the M-1, and here we got an M+1. We'll talk about these in a second. So only the cations are deflected by the magnetic field, yeah, and the deflection depends on the M/Z. So herein, yeah, we have a molecule. This is benzene, and we can see that the highest peak is also the molecular peak at M/Z equals to 78. However, if you look closely, you can see that, yeah, 93.4% of all this molecule is of course that due to, yeah, the highest abundant isotopes of carbon and hydrogen, while you have another species, 6.5% of the species is one that has carbon-13 present, and of course you can see 0.1 would have a deuterium. So you can imagine that 6.6% will be a M+1 peak. See, 6.6% of your sample would be M+1. Herein, you can see, for example, if we're looking at the halides, we have these M+2 peaks, and the M+2 peaks is a 3-to-1 ratio for chlorine, because, yeah, in this case here you can see that the chlorine, yeah, has a 3-to-1 abundance, 35 relative to 37. The bromine, on the other hand, you can see a 1-to-1 peak, yeah, of the 79 to 81, yeah, because those are approximately 50-50. You can see loss of the halide realizes, yeah, the 77 peak. So that fragmentation here. Same thing here. See? the loss of the 35 peak or the 37 peak realizes the M over Z equals to 77 mass units. Look at this one. This is the species that has a benzyl carbon. And the fragmentation takes place, and so you'd expect our fragment to be the benzyl cation, which is 91. But the benzyl itself rearranges to give us a very stable fragment in the chamber, and this fragment is called the tropylium ion. It's a 7-membered ring with 6 electrons in that ring. Yeah, all right. All the carbons are sp2 hybridized. This is an aromatic species, and we'll be looking at that later on. So this is your molecular ion here, 120, but note the base peak, i.e. the most abundant peak, 100% relative intensity, is at 91. For alcohols, you can see that in this case here, alcohols, you can see in this case, with primary alcohol, we see very little of the M plus peak, but we see quite a bit of the M minus 18 peak. The M minus 18 peak, if you see that, you know immediately that you have an alcohol, because that means you lost water. There's also alpha cleavage that can occur. Remember, alpha cleavage is the loss of a function of a group that's close to where your functional group is. So identifying these fragmentation patterns takes practice. Let's have a look. So for example, we look at the nitrogen rule. If your species has an odd number of nitrogen, then of course we'll have an odd number for our M over Z mass units. Alright, now in this class we'll be only looking at compounds with only one nitrogen, so we can always forget about those things. So if you see an odd number for your molecular mass, you know you have nitrogen present. Yeah, we can use high resolution mass spec, and you can see in high resolution mass spec it's quite easy to deduce the difference between these two guys here, which have similar molecular weights, but if you probe closer with mass spec you can see the difference. Degrees of unsaturation is quite nice because it will tell you exactly how much degrees of unsaturation is present in your compound, so you can talk about rings, etc., etc. Yeah, we can do a few examples like this in class, but remind yourself, yeah, this is something that you did before. You find what your parent alkane was, yeah, remove what the hydrocarbon equivalent is, and then you'll have your hydrogen deficiency, and then your hydrogen deficiency divided by 2 will give you your degrees of unsaturation. Remind yourself that the halides all are equivalent to 1 hydrogen. Oxygen being present, you do not count, it's like 0 valent, and 0 hydrogen, and nitrogen is a -1. For group 7 elements, yeah, remember you subtract 1. For nitrogen you add 1, and for oxygen there is no need for corrections. So let's redact what I said on the last slide. So in this case here, you can see that is you add 2 here, yeah. So could you calculate those for me, please? So herein we have this 2,2-dimethylpropanone. I want to know what the fragments are. Yeah, you can see here there's a fragment here at 56, I think this is. Alright, and then try to figure out where this one is from your PDF. You can see that 57 peak is due to the third butyl. Very, very stable carbon. You realize that. So this is the fragmentation right here. What about this one? Yeah, you can see that this is 2-methyl-pentan-3-ol. I want you to pause and review this on your slides, and then we get back to it. You can see that really we haven't seen the loss of water, but we can see quite a bit of alpha cleavage here and here to give us peaks at 59 and 73. So remind yourself, nitrogen rule, higher resolution spectroscopy, and degrees of unsaturation. What about this one? It's a very interesting species. But of course, you can do this by the molecular ion and then think about what appears here and here. That's important to you. So the next time we have a chat, we'll be talking about NMR spectroscopy.